Hello! Well, it's been such a long time since I made a physics or technical related video that I thought I'd have another go at one today. So I'm in our ensuite bathroom, and that's the view to our neighbour's lovely new log store that they just had built. And this is our electric shower. Now, over the last year or so, it's been getting gradually unreliable. It's got two power settings, the low power and full power. And it started so that occasionally it wouldn't work on full power. It would only give you half power even when on the full power setting. And it would gradually do that more and more often. And then over the summer, it deteriorated so that wouldn't work at all and it would only go on low power. And then occasionally it started not even doing low power either. And I thought initially maybe it could be a heater element, but that would probably just fail completely and not be intermittent like this. So I didn't know whether to call a plumber or electrician, but I decided I'd try and call a plumber. It's been really quite hard to get a plumber to just come and have a look at it. They want to come out and they'll actually do something, but all they can do really is buy new parts for it. The diagnosis is going to be quite tricky, or they quite happily will maybe put in a new one. But putting in a new one would entail, all sorts of other problems. Like I don't even know where the stop valve is, don't know where the wiring comes in, might need retiling, like a whole bunch of other things, when basically the shower works okay but just won't go on to full power. Now, if they were to get replacement parts, well, the problem is this doesn't seem to have any replacement parts available from Bristan anymore. They stopped selling this a while ago, and obviously they don't make enough parts to carry on doing it. So I thought I would have a go at diagnosing it myself before I finally get a plumber to come and fit a new shower. But I didn't want to go poking around in my own shower in case I broke something or caused a flood or something like that. So I bought off eBay a second-hand broken shower of the same sort, which even came with a handy instruction manual, so that I could take it apart and see how it worked and then maybe figure out what was wrong with mine. Because I had a suspicion that maybe there was something wrong with this switch, possibly. But anyway, let's get this one apart so you can see what's inside it. So there's two screws here on the bottom, and there's another two screws here on the top. And with the screws removed, the front cover just sort of lifts off like that. And oops, here we go. And you can see there is a little black rubber trim around the edge here, which is to seal it and keep the water out, because obviously this is all inside the shower cubicle. And this is the controls, and they're attached by a little ribbon cable to a connector down here, which we have to pull off the main board. Let's see if I can do that. There we go. So that is the front cover, which is all separate now, and this is the rest of the unit. So let's just give a quick look at how it works. I'll do it sideways because it's easier to fit in the screen. So the water comes in here. This bit can actually flip over either side, and this can point upwards or downwards, so you can have the water coming in either way. My shower actually comes in from this point here. But anyway, the water comes in through this tube here. There's a water filter which you can take out, but obviously you have to stop the water flow first. Comes in here. This here is the control for the flow of water, which actually adjusts the temperature up and down by increasing or reducing the flow of water. That water then goes into this unit, which has the heating elements in it, and it comes out. There's actually a tube inside it that comes back down the inside of it and comes out through this pipe here, and that goes onto the shower attachment. Now, so that's the water side of things. There's also, I believe, this switch here. I think there's something here which detects whether there's actually any water pressure and closes this water switch, but I haven't seen that in operation, so I'm not completely sure. This thing here is the water solenoid, which actually starts and stops the main flow of water. So normally that's closed off so no water comes in from the mains, but when this is energized, it lets the water flow through. So that's the water side of things. Now the electrical side, the mains wiring comes in to here, so you're live and neutral, so live neutral, and there's earth in the middle. The neutrals are all common together, but the live goes firstly to here. This thing, I believe, is a kind of over temperature switch, which switches all the heating elements off if the temperature gets too hot and lets them cool down, and then switches them back on again. So that feeds the live onto the circuit board here. And then there are two relays for each of the two heating elements which are in here. So there's the main element and then the additional element for either 5 kilowatts or 8.5 kilowatts. And then these two relays switch those on and off. And this is all the main circuit board, and the rest of the circuitry is on here. So my first thought was that it might be something to do with the switch here to decide which heating elements are switched on. So let's take this circuit board off and we can have a quick look at what's under there. Turns out it doesn't need all of the screws taking out, because this one here, all it's doing is holding this black bit of plastic on, which is kind of a light guide for the LEDs that are underneath it that show the temperature display. So anyway, looking at this, there's like no switches or anything. It's a lot more complicated than you might imagine. There's a ribbon cable which goes to the main board. This looks like a great big microprocessor, huge microprocessor considering it's a shower. This looks like it might be an in-circuit programmer or something like that for it. And then these are the switches. And I couldn't really figure out what this was doing, but on the one that decides whether it's one or two heater elements, all there is this piece of metal attached to the switch, and that moves around and covers over various plates here. So it looks as if there's a sort of capacitive switch arrangement with this sort of ring in the middle, and then 1, 2 or 3 positions for the switch to be. And that's what the microprocessor decodes to decide how many heater elements to use. And it looks as if there's a position, similar thing for this one, which is actually the water flow rate, but is also the temperature control. There's no piece of metal on this one, but presumably a different shower version could have a piece of metal and have something similar, which can tell the processor where that control is actually located, and maybe kind of do something about adjusting the temperature, because there's no real temperature sort of control. It's just, this just measures the temperature, and I presume maybe if the temperature goes too high it will switch it off, but there's no adjustment of the temperature other than just the flow rate and how many heating elements you've got switched on. So there's clearly nothing wrong, well, nothing obviously wrong with this. There's no switches to go wrong. So that was the first theory out the window. So the next thing I had to look at was, these. Well, the first obvious thing might be that the heater elements themselves might have burnt out. So what I did, I'm not going to bother doing it on camera because it'd be too fiddly, but what I did is I measured the resistance between the connector for the heater and then the common connection down there, and both of them showed not exactly continuity, but they're about 12 ohms for one of them and 10 ohms for the other. I think, I can't remember exactly what they were. Oh, that shows when it was made, 2016. Okay, so this one was 2016. And this one is a 10.5 kilowatt rather than the 8.5 kilowatt that I've got. But anyway, the heater elements, there was nothing wrong with them. So the next thing was going to be see if I could take this circuit board out and figure out how it worked to see if there's anything wrong with that. This bit here, just out of interest, this bit, I thought this was just an earth connection, but this wire actually goes to a thermistor, which is kind of buried in here and measures the outlet water temperature, which is then goes via these wires out to the microprocessor and displays the temperature on the display. But anyway, what I had to do next is take out these screws to disconnect the wiring, and then take these screws out. There's one there, and there's another one just down here to loosen this circuit board, and then had to unplug that. I also had to unplug this micro switch, and then there's another wire on here which actually goes to the inlet solenoid. Had to disconnect all of those to get this out. Okay, so this is the main circuit board, and I'll try and give you a quick run through of to what connects where, and then I'll go through the circuit diagram as I decoded it. So anyway, this is the live neutral coming in, goes through this resistor, which acts as kind of a fuse or current limiting resistor. Then it goes through this capacitor, which is a 680 nanofarad capacitor, supposed to be. It goes to down here, you might not be able to see it, that's the bridge rectifier, which then charges this capacitor. and that gives some kind of a power supply, and then it got very difficult to decode, but I'll show you in a minute. Anyway, this is the two relays, these two to power the main heating elements, and this is the relay that powers the inlet solenoid, and I think it's these two transistors power this relay, these two power that relay, and there's two transistors down here that power this relay, and they have a couple of diodes across each relay, well, a diode across each relay, which is not quite what you'd expect, which would be the diode to prevent sort of back EMF damaging the transistors. But again, I'll show you that in a minute. And then there's a whole bunch of circuitry here, which I've kind of drawn a circuit diagram of, but I cannot really figure out what it does. This connector here goes off to the switches, and this connector goes to, or two pins go to the little micro switch that I think tells whether there's actually water pressure, and then there's two connectors that go to the thermistor to measure the outlet water temperature. And then these are the main connections to the heating elements, which is why they take a lot of current. They take about 20 amps each at least. This is the main live incoming from the temperature sensing switch, the over temperature switch, and then this is one heater element out, and then this is the other heater element out. So that's roughly what the circuit does, and you can have a quick look at the underneath as well. So you can see there's lots and lots of common connections here to give them a lot of current carrying capacity, and then this is the sort of low current control circuitry. So I'll show you what I came up with from the circuit diagram, and that will give you an indication of what I think went wrong with it. So here's the first page of the circuit diagram, the simple part, which is the incoming mains. So live and neutral goes through this 330 ohm resistor, 680 nanofarad capacitor, the dropper capacitor, to a bridge rectifier, and then a 100 volt 47 microfarad capacitor. There is then, I've drawn this sort of chassis thing to show this kind of back plane, which normally you'd think, oh, that's obviously the negative voltage of the supply, but it really is a bit weird because this capacitor is connected to it, but this one isn't. And this one then connects to another 200 ohm resistor, which is somewhere in here, I think. It's behind the capacitor. You might be able to see it there. That's the one. This 200 ohm resistor to a kind of negative supply to the relays. And then we have a 15 volt Zener diode and a 5.6 volt Zener diode, which are then connected to this. So effectively you've got about 20 volts across this capacitor, and there's another capacitor across here, and this one seems to be a 5.6 volt supply to the control circuitry on the switchboard. And this is some kind of positive supply plus 20 volts to something, not quite sure what. Anyway, so that's the main part of the circuitry. The next bit that I decoded was how the relays work, and they don't work in a very obvious way at all, because rather than the transistor switching on the relay, the the negative voltage from the power supply that I showed you comes through this 200 ohm resistor and then goes in series to all three of those relays and then connects to this chassis point. So if none of these transistors were here, all of these relays would switch on. The diodes, they're not the back EMF protection diodes, they are actually, well, two 24 volt diodes, because these two are 24 volt relays, and a 12 volt Zener diode, because that's a 12 volt relay. So these are Zener diodes with different voltage ratings rather than just back EMF diodes. They will work as a back EMF diode because they're connected the correct way around, but that's not quite what they're doing. So they're basically limiting the voltage across each relay. And then to switch off the relay, these transistors, that one, or that one, are switched on, which will basically short circuit the relay and prevent it coming on. So that means that basically the current from the power supply goes through all the relays or bypasses the relays through the transistors. And depending on which transistors are on, one or more of the relays are on. And it's a bit of an odd situation, but it does mean that you only need a certain amount of current and it should switch on all the relays. And it doesn't matter whether the relays are on or off, you're still taking the same current, which means that the dropper capacitor, which can only supply a certain current, should allow it to work. Anyway, these transistors here because they're on a negative voltage supply, they have to be level shifted by these PNP transistors so that they can be operated by pins from the control circuitry, which is powered from the 5.6 volt supply. So there's basically a pair of transistors for each relay. And that bit is relatively straightforward. That's connected to the control circuitry on the switch board on the front panel. There's a little bit more. These are the Zener diodes again, and this is how the headers are connected. There's a few pins connected to various places on the white header and the black header. And then the final bit, I'll just show you what I got for the circuit diagram because I can't figure out what it does, is this bit. There's a whole bunch of transistors down here and 2 electrolytic capacitors and some double diode packages, double Schottky diode packages, and they're connected like this, but they don't seem to have any control output or control input or do anything. I mean, it kind of looks as if it's like a voltage doubler, maybe, but I can't tell what it's doing. Something to do with the power supply arrangement, but I really haven't got a clue exactly what it's doing. If you can tell me, then brilliant. But anyway, I've put that in there, but it really doesn't matter from my point of view, because what I thought was the capacitive dropper circuitry is supplying the current to make these relays work. And if it can't supply enough current, then the relays may not turn on because they're basically taking all the current from the capacitor, and if there isn't enough, they may not switch on. And I measured the value of this, and it says on the side, if you can just read it, I'm not sure whether you can read it, 684K. So 684 is 6, 8 and 4 more zeros in picofarads, which was 680 nanofarad. I measured it in circuit and it was only about 400 nanofarad, which means it's significantly less than it should be. And that means it won't be passing as much current as it should be. And I had this theory that maybe it's not passing enough current for the relays to reliably switch on. And if the mains voltage happens to be a bit low one day, then maybe it won't work. And if the mains voltage happens to be a little bit higher, then maybe it will work. And that was kind of how the fault was exhibiting itself. In fact, Big Clive made a video about 10 years ago showing exactly how this type of capacitor failure happens. I'll leave a link to it in the description. So what I did, this is getting to the end, what I did is I got some more capacitors, and in my real shower, I soldered down to here, to that point there, to where this bridge rectifier connection is, and then the other connection to the capacitor is just there on the resistor. And I soldered a 200 nanofarad capacitor across it. Well, actually, I measured the capacitance of the capacitor in my shower first, and it was only 380 nanofarad, so it was even lower than this one. And so I soldered another one across it, and to cut a long story short, basically that fixed the shower. So you can see when the shower is running, now it's using 8 kilowatts. Well, actually, it's only using 8.19 kilowatts. It used to be 8.5. I haven't got any way of measuring the mains voltage at the minute, so it might be a bit low. But anyway, it's more than 5 kilowatts. But anyway, at the end of the day, I've soldered in another capacitor. I had to buy another couple of X2 capacitors. Capacitors from RS, no cheap eBay rubbish. So proper X2 capacitors to parallel across it. So there we go. That's the solution to this problem. If you happen to have the same shower and a similar problem, then you know what to do.